Hello, everybody. My name is Kyriakos Muratidis, and I will be presenting the paper Marrying Top K with Skyline Queries. This is joint work with Keming Lee and Bo Tang. So when it comes to identifying records of preference in situations where multiple objectives are to be served, meaning that these records are having multiple attributes that we have to define our preference on, there are two common paradigms used for that task. The first one is the dominance-based, in which case, if a record has higher attributes on all dimensions compared to another record, then we say that the first record is dominating the second. So if we select those records from a data set that are not dominated by any other record, then we're simply getting what is commonly known as the skyline of the data set. This has been generalized also to the K-skyband set, where basically we are selecting those records that are dominated by fewer than K others. And this is the first paradigm. An alternative paradigm is to rank records by utility. So in this situation, if we assume a two-dimensional example, meaning that our records have two attributes, the user is supposed to input a preference vector W that has two weights. Now, each record in our database, in our data set, as I said, has two attributes and is now associated with a utility score or a utility value, if you may, that is equal to the weighted sum of its attributes. Now, this way, every record is associated to a utility score, and therefore we can rank them and just keep the top K to present them to the user. This is the standard top K query. Now, both these paradigms have some shortcomings. When it comes to the Skyline, first of all, it is not personalized. This means that every user is going to receive the same Skyline records. The second thing is that we don't have any control over the size of the Skyline. When it comes to the top K query, now the weak point of this one is that the input preference vector W, whether it is directly input by the user or mined with some preference learning technique, it is just an estimate of the actual preferences of the user. However, this standard top K query is too rigid on its ranking with regards to the input preference vector W. So in this work, we're having three strong requirements. First of all, we want to produce personalized results for our user. Second, we want the user or application to be able to dictate, to control the size of the shortlisted records, the number of the shortlisted records. We call this output size specified operator, and we refer to it as OSS for short. Now, it is based on a principle that is known since the 50s, it's the Hicks law, which suggests that to control the number of results presented to the user is essential in order to support effectively her decision and to achieve a good user experience. And this has been the cornerstone in designing e-commerce applications. Now, the third strong requirement that we're having is that the preference specification must be flexible, which juxtaposes with the rigid ranking offered in the standard top K query. So the approach that we take, first of all, is in order to achieve our first strong requirement, that of personalization, is to employ utility scoring according to a preference vector W, which preference vector W, there is a large variety of options that we have on how to mine it in the preference learning area. So there are ways to mine it, but then we do not take it as rigidly as the standard top K query. Instead, we allow it some flexibility. We allow it to relax. How do we achieve that? Well, instead of just taking it as a vector, we allow it to expand on all directions in its domain. Therefore, we are turning it from a vector into a hypersphere of possible preference vectors, which has a gradually increasing radius rho. Now, to achieve output size control, what we're doing is that we're expanding this hypersphere incrementally, and we stop when the number of results we have collected is the desired number, say M. This M is specified by the user or application. Now, to compare with the previous multi-objective queries, of course, I'll have to refer you to the paper, but I'll tell you here that our operators are the only operators so far that serve all these three requirements that I mentioned so far. So the first operator we're having is ORD. Its input, first of all, is a d-dimensional data set, a set of records, then also a estimated preference vector W, which we also refer to as the SID vector, the standard value K, very commonly used one, and the desired output size M. This is how many records the user wishes to see in the output. Now, for the expansion, what we do is that we consider preference vectors that are within a radius rho from the input SID vector for a gradually increasing rho. This refers to the expansion process. We also define the notion of rho dominance. We say that a record rho dominates another record if its utility is higher for every preference vector within distance rho from the SID. Now, what does the ORD output? It outputs the rho skyband, meaning those records that are rho dominated by fewer than K others, for the minimum rho that produces M records in the output. Two important notes here. First of all, that this stopping radius rho, this minimum rho required to produce M records in the output, is unknown to our algorithm in advance. Second, the user and the application do not need to be bothered with the value of this rho. The only thing that the user or application needs to specify is how many records they need in the output. So for the second operator we propose, which we call ORU, the input is the same as ORD, the expansion process is the same as ORD. However, here we're reporting those records that belong to the top K result for at least one preference vector within distance rho from the input SID vector W. And all that for the minimum rho that produces M records in the output. Once again, this stopping radius rho is unknown to the algorithm in advance, and the user and application do not have to mess with it or do not have to bother about it. Now, something about our ORU algorithm is that it is going one step further than the standard definition of ORU, and furthermore, it even produces the specific order-sensitive top K results for every vector within radius rho from W. This is a plus point here achieved by our algorithm beyond what the definition of ORU requires. One important note for both our ORU and ORD algorithms is that they require absolutely no precomputation. They only need a general purpose index, such as an R tree built on top of our dataset, on top of our records. So for the ORD solution, the first observation is that naturally the only records that are dominated by fewer than K others could partake in the ORD result. Therefore, the only candidate records we have are those of the traditional K skyband. Something here to introduce the notion of the preference domain, well, this is the domain where the preference vectors fall. So in this situation, we have a three-dimensional scenario. And if we normalize the preference vector so that the sum of its coordinates is 1, then this means that basically the preference vector can be represented by a point on this rectangle that I'm showing you here. In general dimensionality, it's going to be a simplex. Okay, now let's consider two options, R1, Ri, and Rj, where they don't dominate each other. And let's assume that Ri has a higher utility score than Rj for the input SID vector W. Now, the equation that the utility of Ri equals to Rj actually divides our preference domain into two parts. Here is this hyperplane defined by the formula that the utility is the same. And this is the divider of your preference domain of your triangle here into two parts. In this part that includes W, the utility of Ri is stronger than Rj. So if we compute the minimum distance rho ij between the seed vector W and the divider, okay, we know that Ri is gonna rho dominate Rj for any vector that is within this distance rho ij from the seed vector. You can see this visually here. If you take this minimum distance, and since in this entire part Ri scores higher than Rj, then for a hypersphere centered at W with its radius rho ij, Ri is gonna rho dominate Rj. Of course, the hypersphere in this situation, since we're talking about a triangular preference domain, is actually a circle, okay? It's not a sphere, it's a circle, but in the general case, we're talking about a hypersphere. So this way we have managed to sort of formalize what happens with a pair of records when the one rho dominates the other. So if we focus on just one specific record and consider all the other candidate records, meaning all the other K-Skyban records against it, by finding this kind of minimum distances that I explained in the previous slide, effectively we are mapping all the competitors of this guy Ri, we're mapping them into intervals where these competitors are rho dominating it. Therefore, if the input k equals 5, we can find the rho value past which my record Ri is going to belong to the rho skyband, meaning it's going to be rho dominated by fewer than 5 others. So we call this radius here the inflection radius of Ri. The idea is that if we compute the inflection radius for every K-Skyband record, then we can have a representation of the rho Skyband contents for each and every value of rho. Observe here what's going on. Each and every of my candidate records is mapped into an interval in which it belongs to the rho Skyband. So all I need to do, if I need to produce m records in the output, let's say m is 8, I simply need to take the 8 such intervals that start at the leftmost positions. So basically, these 8 intervals are going to tell me what are my ORD results. In the paper, of course, we're having an optimization where you don't need to compute and consider the entire K-Skyband, which reduces the computational cost quite a lot. So efficiency is one of our main objectives. Let me then start describing briefly our ORU solution. Over here, we're starting by the concept of the convex hull of the dataset. Now, if we focus on these facets of the convex hull whose norms are positive, okay, we're showing these facets in blue here, and their norms are these vectors v1, v2, v3, v4. Well, only the records that fall in this blue part of the convex hull, which we call the upper hull, only this can be the top one option for any possible weight vector. Effectively, what happens is that these norms here are partitioning my preference domain, which in this two-dimensional example, the preference domain is just this diagonal line segment. So this preference domain is partitioned according to the representations, the dual representations of these facet norms. For any preference vector within, for example, v2 and v3 here in this interval, the top option is going to be record R3. Therefore, we call this the top region of R3. We can, of course, define the same thing, the same kind of partition for the second upper hull layer. This means that if I take away, if I remove the upper hull layer records from my dataset and I compute the upper hull layer in the remaining records, then the upper hull I will get is the one shown here in blue. This is the second layer, as we call it, of the hull. Now, similarly, the facet norms in this second upper hull layer also partition my preference domain into another set of top regions. So let's focus on the top region of R3. Now, R3 belongs to the first layer. So we know that the top one record for any preference vector inside the top region of R3, of course, is going to have R3 as the top one record. Let's see what happens, however, with, okay, we have preference vectors in that top region of R3. What happens with which records are possibly the top two, which may rank after R3? Well, these candidates come from two sets. Either those that are adjacent to R3 in the first layer. Here is my R3. This is the first layer partition. The adjacent ones are R2 and R4 in the first layer. And the second set where my candidates for the top two position could be coming from are those of the records in the second layer that have top regions that overlap with the top region of R3. Well, these records turn out to be the ones in blue here. So basically, anywhere in the top region of R3, we know that the top one record is R3. And when it comes to the top second one, the candidates are this, and this. So these five records are the only candidates to be ranking number two after R3. We can actually generalize that. So if in a region R in the preference space, we know the top one, that the top I result, and if we assume that the nth is the deepest layer that any of these top I results falls in, then we are proving that the top I plus one record anywhere in this region R must fall in the union of either the adjacent records to any member of the known top I result, or among the records in the immediately deeper layer from the one we have seen so far, meaning the n plus 1th layer, whose top regions overlap with the region R. So our solution is, of course, avoiding to compute the entire k layers because that's going to take too much time. And anyway, we don't know the final stopping radius. So what we do is that we start by the first layer top region that includes the SID vector W, and then we're doing an expansion, a gradual expansion in 2 dimensions. Okay, the first dimension is that we expand within the layers that we have encountered so far, and the second dimension is to expand by looking into the immediately next deeper layers. Effectively, what we're doing is that we're incrementally expanding rho, computing all the possible top k results along the way, and we stop when exactly n distinct records are found. And we actually implement this as a branch and bound search in an implicit tree that we are constructing on the fly. That implicit tree, its nodes are effectively top regions in various layers. We have done some case studies which show that our results, the result of ORD and ORU, is different between our two operators, but also very different from existing operators like standard top M or some OSS versions of Skyline. So in this specific example with NBA, only ORU happens to report Trae Young, which is the Rising Stars Challenge player in the specific season where we drew this data from. And one important finding here is that the standard top M is missing Andre Drummond, which both of our operators are finding. And actually, they managed to find it, although it is for an alternative weight vector than the input W, yet a very similar vector to it. So basically, we're achieving our objective to consider alternative yet very similar preferences to the input preference vector W. So we have repeated this experiment using different dimensions of the MBA dataset, and we have found similar findings. And once again, we have shown we have come up with this same finding that our operators report records that are particularly strong for alternative yet very similar preferences to the input vector of the user, something that the standard top K paradigm cannot do. So one important remark is that a very important artifact of this work is the implementation that includes a lot of optimizations that were impossible to put in the paper even. So we have made this publicly available and we have linked it in the paper. Thank you very much for attending the presentation.